All right, let's jump right into this explainer and crack the case of the hidden waste in our thermal systems. Today, we're doing some thermodynamic detective work. We're going to look at where our energy really goes when we burn fuel, and honestly, more importantly, how we can actually stop wasting it. So, picture this. You're filling up your car with gas at the pump. You probably think you're paying for energy, right? Makes sense. But, well, thermodynamics tells us a kind of different story. What you're really paying for is something entirely different. You aren't buying energy, you're buying the potential to do work. Now, you might remember the first law of thermodynamics. Energy is always conserved. It literally never disappears. It just changes forms. But the reality? The potential to actually use that energy to do work is constantly being destroyed. And this useful potential is what we engineers call exergy. Exergy is what actually has economic value. Energy is conserved, sure, but exergy? Exergy is consumed. And in our engines, it's pretty much often just wasted. Here's our roadmap for this explainer. We're going to cover uncovering the exergy concept, measuring exergetic efficiency, defining chemical exergy, modeling Earth's reference environment, and finally, evaluating standard chemical exergy. Let's get into it. Section 1. Uncovering the exergy concept. Let's start by defining our main suspect here and understanding why it is absolutely crucial to our economy. Okay, so the absolutely crucial point is that exergy is the property that actually quantifies the potential for use. Think of it like this. Imagine a small container of fuel surrounded by a massive abundance of air. If you burn that fuel, you get a warm mixture of exhaust gases. The total energy? Exactly the same before and after. But initially, you could have used that fuel to drive a car or, generate electricity. After it burns, that warm exhaust gas is practically useless to us. The potential for work, the exergy, was completely destroyed. To make things a bit easier to wrap our heads around, when we calculate exergy, we visualize a system passing to equilibrium with the environment in two distinct steps. First up, there's the thermomechanical transition. That's where temperatures and pressures equalize with the environment. Second is the chemical transition, where the actual chemical makeup equalizes. For this explainer, we're really going to focus heavily on that second step. Moving on to Section 2, measuring exergetic efficiency. Now, let's look at how we measure the exact amount of this potential that gets wasted in engines and reactors. Let's picture our main crime scene, a steady-state reactor. Fuel and air enter on the left, combustion happens right there in the middle, and products exit on the right. This setup is exactly where we do our exergy accounting. When we track the accounting here, we see exergy entering primarily through the chemical makeup of the fuel itself. Then we track the exergy leaving through the combustion products and some stray heat transfer. But the gap between what goes in and what comes out, that is the exergy destroyed. And here's the real kicker. The highly irreversible nature of combustion itself is where the true destruction of exergy happens. It's not just heat leaking out. No, the chemical reaction itself literally destroys your fuel's potential. Let's actually put a number to this. Take your standard internal combustion engine developing, say, 50 horsepower. When engineers run the numbers, comparing the power developed against the total exergy of the fuel going in, they might find an exergetic efficiency of only 40%. Wow. That means 60% of your fuel's economic value, its actual potential to do work, is completely lost. Gone. Destroyed. Mostly right there in the combustion chamber. Section 3. Defining chemical exergy. To really grasp our fuel's potential, we've got to start defining this concept in some real depth. Chemical exergy exists simply because the chemical makeup of our fuel is vastly different from the abundant, stable air surrounding it. Think about it. As long as there's a difference in composition between our fuel and the natural environment, there's a potential to extract work as the two try to mix and reach equilibrium. It's like a coiled spring of chemical potential. Section 4. Modeling Earth's reference environment. But, to mathematically measure that chemical difference, we have to precisely define what normal actually is by modeling the Earth's atmosphere. So, engineers actually construct a baseline reference environment to represent the Earth's atmosphere. They use this exact atmospheric makeup, roughly 75.6% nitrogen, 20.3% oxygen, plus some traces of water vapor and carbon dioxide. We model all of this at a standard 298.15 Kelvin, which is right about 25 degrees Celsius, basically room temperature, and 1 atmosphere of pressure. This specific model becomes our baseline.
Chemical exergy is then calculated by figuring out how much work we can get by taking our fuel and reacting it until it perfectly matches this exact atmospheric baseline.
And that brings us to Section 5, Evaluating Standard Chemical Exergy. Let's see how this all builds into the standard chemical exergy values of the fuels we use every single day. We set up this really cool mathematical thought experiment. Imagine a control volume where our hydrocarbon fuel enters from the left at the standard environmental temperature and pressure, and at the exact same time, we pull in oxygen directly from our reference environment model.
As the fuel and oxygen react inside this theoretical control volume, we dictate that any heat transfer back to the environment happens exactly at that baseline temperature, T0. We're ensuring absolutely nothing is lost to random temperature differences. It is a perfectly controlled theoretical reaction. Then, as the combustion products like carbon dioxide and water vapor exit back out into the environment, we calculate the absolute maximum theoretical work that could possibly be extracted from this perfect process. The mathematical result of this process gives us the exact chemical exergy value per mole of the fuel. It's basically the ultimate ceiling of what that fuel can provide.
All of that really painstaking thermodynamic modeling gives us incredibly useful data. Engineers don't actually have to run that thought experiment every single time. They can just instantly look up the chemical exergy of different fuels. For instance, methane is sitting at over 800,000 kilojoules per kilomole. But then consider liquid octane, a primary component of the gasoline in your car. It packs a massive 5.4 million kilojoules per kilomole. That is huge. And this brings us right back to the gas pump. This thermodynamic data explains real-world performance perfectly. This is exactly why a vehicle running on an E85 ethanol blend gets noticeably lower fuel mileage than one running on pure gasoline. When you actually look at the exergy values on a mass basis, ethanol simply has about 2/3 the chemical exergy, the true potential to do work, of gasoline. You are literally putting less potential into your tank. Makes sense, right? Ultimately, all of this complex thermodynamic detective work, the reference environments, the chemical baseline models, the exergetic efficiency percentages, it all exists for a really vital reason. As the experts highlight, exergy analysis helps us pinpoint the exact locations, types, and true magnitudes of waste in our systems. It allows engineers to stop guessing and start mathematically optimizing exactly how we use our precious, non-renewable resources. So the next time you look at a thermal system, whether it's a car engine or a massive power plant, try to look past the energy that's just changing forms. Instead, ask yourself, how will you track down the hidden exergy waste? Because the engineers who master this concept, they're going to be the ones designing the hyper-efficient, revolutionary engines of the future. Thanks for joining me on this explainer. I really hope you found this thermodynamic detective work as fascinating as I do.